And we're back. Happy Thursday. Today we will switch gears and focus on a new set of tools, so-called conditional probabilities. But before we begin, let's take care of a few administrative bits. The reading has changed. A new reading by the 17th of September, which is a week from today, Thursday the 10th. In the main text section 2.4, that's pages 26 through 32. As usual, please make sure you're keeping up with the reading. Do a little bit of work every day, about an hour a day for this class. Project 1 is also due this Tuesday on the 15th of September. So do a little bit every day, study like a ninja, and read every day. Okay, so when we last left off, we talked about considerations for counting or enumerating the possible outcomes one might observe for a complex scenario. And we talked about two heuristics to help us. One answers the question, do you replace your selection after you make it? And there are two flavors for this, with replacement and without replacement. We also talked about if you distinguish, once you make a selection, if you distinguish duplicates. For indistinguishable events, the order matters. Does not matter. Let me correct that. For distinguishable events, the order matters. So in the case of birth of two children, male followed by female is not equal to female as the eldest child followed by male as the younger sibling. In the indistinguishable case, what we're looking for is the identity, the fact that one was selected, and not the order in which they were selected. And so in that case, male followed by female is the same as female as the eldest child followed by male child as the youngest sibling. We also talked about combination with replacement. And for combination with replacement, we're going to make a choice of k many objects out of a pool of n total alternatives. And so we have our n objects. Let's draw this out. Let's select blue. We have our n objects. So that's object 1, and object 2, object 3, object 4, object 5, up to and including object n. And in this figure, we have a bunch of sticks, and there are a total of n minus 1 sticks. So a total of n minus 1 sticks. Now, it just so happens if you have n minus 1 sticks or bars, you can count a total of n spaces. So there's the first space, the second space, the third space. And let me draw these spaces using these kind of angle brackets, almost like they're bins, jars, or urns. And you have a total of n of these bins or spaces. And these spaces are the spaces on the left of a stick or on the right of a stick. So here's my first space, my second space, up to and including my nth space. And so it just so happens, as we said before, you're going to throw a ball, and that ball is going to land in one of these spaces. And so when we represent the object you're going to choose, that pool of alternatives from which you make your selection is represented by each of these n many spaces. Now the balls, we're going to throw a first ball, a second ball, a third ball, up to and including a total of k balls. So we have a total of k balls that we're going to throw. Now these k balls can occupy one of these n many slots, and when we get a ball in one of these n slots, that means that you are selecting that nth item, from among those n many alternatives. And so if a ball lands, say, in this space here, where the 2 is, that means you selected the second item. If a ball lands in this first space, that means you selected the first item. And so the fact that there's no restriction on the pool of alternatives, every time you throw a ball, that ball can land in any one of these n many spaces. So that means if you have no preference for any one of these objects and you have k different balls you're going to throw, you make k choices from among these n many alternatives. And you're going to do so with replacement, because when you throw the first ball, let's say it lands in the bin 2, that's the first ball. When you throw the second ball, you still have all of those n many alternatives to choose from. And so what can happen then is that you can have more than one ball associated with each one of these bins or slots or positions representing one of these n many choices. So we throw these balls. In this figure above, we have our first alternative is selected twice because we have two balls. Our second alternative is selected once, okay. Our third alternative, that third slot, is not selected at all, so 0. Our fourth alternative in this example is selected 3 times, and so forth. And so how we imagine this selection with replacement is if we count up all of these items that we've drawn. We said we throw k balls, okay, and we also said we have n minus 1 of these bars representing the n bins or the n spaces. Okay, so if we were to count all the objects that we have a total of k balls, and we have a total of n minus 1 of these bars or sticks. Okay, so if we're going to add up the total number of items that we have, that would be k plus n minus 1. Now, of course, depending on how you arrange these k balls and n minus 1 sticks, it's going to represent some selection of k alternatives from a total pool of n many choices or outcomes. Okay, so if we look at a particular way of arranging these, well, that's just a permutation. And if we arrange them, every time we arrange them, well, we reduce the size of this k plus n minus 1 items. So let's say we wanted to build this particular arrangement that we see. Well, the first thing we do, we select a ball. Okay, if we select a ball at step 1, we put that ball down, and at that point, we have k plus n minus 1 minus 1, right? Objects left. And then at step 2, let's say if we selected from these, if we're going to arrange these in all of the possible ways we can arrange them, we selected, to be consistent with this diagram, we selected another ball, right? That's now k plus n minus 3. And then step 3, we select that stick. Okay, that's now k plus n minus 4. And so essentially, when we think of or consider all of the possible arrangements of these balls and sticks, well, that's nothing more than a combination without replacement. And we said our combination, our arrangement without replacement, was the number, let's call that A, right? A choose k is equal to A factorial over A minus k factorial. Okay, and that's what we said. That's permutation without replacement. And now when we think of this with replacement, that's what changes things. Now, what happens is, let's say we made some arrangement here. Let's look at the arrangement that we have in this figure. And I'll just draw a box around it to direct your attention. Now we have, in this figure, we've selected the first alternative twice, the second alternative once, the The third alternative, not at all. Fourth alternative, 3 times, etc. Now we have here K balls. And let's now label those balls so that we can know which ball I'm talking about. So if I call that ball B1, B2, B3, B4, ... the last ball would be B sub K. Now, of course, if I had my balls, it doesn't matter which ball is in which position. There's no distinction. And so while I have an ordering within this arrangement of B1, B2, B3, B4, up through B sub K, it's the same problem if maybe I said B2 is here, B1 is here, B3 is there, B4 is here, etc. So that means I can arrange my K many balls any way I want to. It's a duplicate if I have the ordering listed in this figure, B1, B2, B3, B4, etc. Or if I said B2 followed by B3 followed by B1, B2 followed by B3 followed by B1, etc. So how many can I arrange my balls? Since I'm not distinguishing the arrangement of the balls that I place in each, 2 of them here, 1 of them here, 3 of them there, I have K factorial of them. And so here, when I look at this combination with replacement, this part, K plus n minus 1 quantity factorial over n minus 1 quantity factorial, that talks about the permutation without replacement or combination, that selection without replacement of the sticks and the balls. And now once I have a particular arrangement of the sticks and the balls, I have K factorial duplicates that I need to factor out, and that's where that 1 over K factorial comes from. Okay, so please take a look at this on your own and convince yourself that why this is the case. All right, so let's begin with a little bit of a warm-up. So we have this thing called a random variable, and a random variable takes an event that you observe, and it measures something over that event. A random variable going forward will be the quantity of discourse that we consider when we talk about probabilities. This when can I see you again? So a random variable measures events or sets of objects or observations whose outcomes are uncertain. So one question we might ask with a random variable or measure, how many possible objects do we have? Or how often does a particular object or set of objects occur? So let's begin with this example. Let's define T for tennis ball. And T is going to be a random variable, abbreviated R period, V period. And this random variable T is going to measure the number of tennis balls of a given color that you're going to pick from a bin while blindfolded. Now, it's important to note that you're blindfolded because you're not going to prefer a particular bin. You have no control over that. You're just going to pick from some bin, not preferring one bin over another. So it's the number of tennis balls of a given color. So here is an example. This is a bin, and now you can't see what's in the bin. I'm just showing you what's in the bin in order to demonstrate the concept. We have the probability that some random variable, like T, is equal to some value, like the color of a ball, is computed as being the number of items that have that value, that's the number of favorable that we talked about, over the total number of items. That's the total number of outcomes that you can measure in this case. So here we have a bin, and we have 3, 6, 9, total of 12 balls in a bin, 4 by 3. And so we have 12 balls. And so in one case, we're going to ask the question, if you were to pick a ball out of this bin, what's the probability that you would pick a yellow ball? Well, what would you do? all right, you'd say the number of favorable for yellow is 1, 2, 3, 4, 5, 6, 7. That's 7. And the total number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is 12. So the total is 12. We express that ratio, that's 7 over 12. Okay. What if we were to compute the probability that the number of balls the number of balls you have being green, number of green balls? Well, number of green is 1, 2, 3, 4, 5. So the favorable for green is equal to 5, and the total is equal to 12. Okay, so that's equal to 5 12. All right. So, and there's our answer. So we compute, in this case, our probability by expressing what we had discussed before, the number of favorable objects over the total number of objects. All right. So let's make this a little more complicated. We have a number line, and we're going to place our balls over the number line, and we're going to separate them out into individual bins. And so here we have 4 bins: the first bin, the second bin, third bin, and the fourth bin. And each one of these bins is going to sit over a number. So this bin sits over the number 1. The second bin sits over the number 3. Third bin over the number 5, and the fourth bin over the number 7. Now, we're going to take each of these tennis balls, and we're going to label them with a number. So every ball in bin 1, we're going to get a magic marker and write on this tennis ball the number 1. Every ball that came from bin 3, we're going to write a 3 on each of these tennis balls, and so forth for every single bin and every single ball in this example. So these would be labeled with 5, I have 5, another 5, and lastly, the single ball in this last bin will be labeled with 7. So now, what if I were to ask the question, instead of random variable t to measure the color of a tennis ball, I have a random variable b for bin, which says the number of objects that have this bin label 3. So it's a label 3. Okay. So if we were to do this, we'd say, okay, well, again, what's the number of items that are favored? So favorable is equal to, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, equal to 10. And the total is equal to, so that's 10, that's 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Total is 20. So the favorable over total, that's 10 over 20, which is equal to 1/2 or 50%. Okay, so, and there's our answer. So we can compute this probability quite readily, and it's just that scheme for the random variable. Instead of being the raw outcome, it's the outcome from some random variable, where a random variable is a measurement over an event. Okay, so what happens if we take some of these tennis balls and we put in some green tennis balls? Again, we still label those tennis balls in bin 1 with the label 1. So you have some yellow tennis balls with a 1, and you have a green tennis ball with a 1. Likewise, every ball, regardless of color, in bin 3, you're going to get a magic marker, and you're going to write 3 on that tennis ball. Okay, so now we do that for every single ball again in every single bin. So for bin 5, we write 5 on that ball, regardless of if it's green or not. And we're going to have balls that are green in this case and balls that are yellow. And we're going to write a 7 on that last ball that's in bin 7. So now let's say we put all these in a bag, or we're going to randomly pick one, not favoring any one bin over another. If I were to ask what's the probability of picking a green ball? Well, again, it's the number of favorable objects, and that number of favorable is 1, 2, 3, 4, so that's 4 that are green, and the total is equal to 20. That's 4 over 20 is my probability. which is the same as 1/5, which is equal to 0.2. All right, so, or 20%. So again, regardless of the random variable, here we have a different random variable. Instead of B for bin, we have T for the color of the tennis ball, and we can compute that as the number favorable over the total number of objects. Okay, so now, what if we are concerned only, not about all the balls from all the bins, but we're only concerned about some of the bins and not all of the bins? So a conditional probability is the mechanism that we use to do this. And you can think of a conditional probability as a kind of probability with filtering. And so how you express a conditional probability is as follows. You say the probability that some variable equals some value, vertical bar, given that some other variable, random variable, takes on some other value. And how this works, or how you pronounce it, is you say the probability that variable 1 equals some value, given that variable 2 equals some other value. So that's how you pronounce it. And so the semantics or behavior of a conditional probability is this kind of filtering or setting aside of objects that you consider for all of those measurements associated with this expression on the right-hand side of this condition bar. For all those objects for which that condition, that variable equaling some value, is true, you're going to set them aside. So when you set them aside, what happens? I'm going to use the term universe of consideration to refer to all of those objects that you use your pool of possibilities when you're trying to calculate a probability. And so when you set aside objects in your universe consideration, so here's my universe. Let's say it's sample space omega for die. And my universe of possibilities is 1, 2, 3, 4, 5, and 6. And so if I said, given that, for example, the number of dots, the outcome is even. So if it's even, I set aside and eliminate from consideration those that do not satisfy my condition, all right, which is this thing on the right-hand side of the condition bar. So as I said, given the number of dots is even, well, I don't consider the 1, I don't consider the 3, I don't consider the 5. What am I left with? I'm left with a new universe of consideration, which is equal to the set of objects 2, 4, and 6. So now, if I were to say the probability that the dots, the outcome, is a 2, given that I know the number of dots is even, now when I express my probability, the number of favored over the total number, this total number is going to change. It's no longer the cardinality of omega die, right, which is equal to 6. It's now the cardinality of that altered sample space. My universe of consideration has changed. It's now this magnitude or cardinality of the set 2, 4, 6, which is equal to 3. So now when I compute this new probability of the 2 outcome, given that the number of dots is even, my favorable is going to be 1, number favorable, because I only have one item, 2, that's 1, over the cardinality of that new universe of consideration, 2, 4, 6, which is just equal to 1/3. So one of the things conditional probabilities do, you'll notice, if I just had, without any restrictions, nothing given, no filters, if you will, my probability of getting a 2 would equal 1 over 6. But if I know that this condition is true, given that the number of dots is even, that changes my universe of consideration, and the result of that is an increase in the probability. Instead of being a probability of 1/6, which is 0.1667, it's a probability of 1/3, which is 0.3333 repeating. And so my probability has increased as a result of what I'll call new information. And so this filtering probability or conditional probability, its purpose is to allow you to evaluate a probability if you have new information. Okay, and so let's take a look at this example. And what if I were to ask you, not just is the probability, what's the probability of selecting a green tennis ball, but which we saw from before is 4 over 20 or 0.2 or 20%. What if I were to tell you, what's the probability of picking a green tennis ball given that only those labeled from bin 5 were going to be in your selection? So maybe I dumped everything from bin 5 into a bag and had you close your eyes, reach into the bag, and pick one. Well, your universe of consideration is now different. You no longer have 20 objects. You have 1, 2, 3, 4, 5 objects. So now, given your 5 objects from bin 5, that's your new universe of consideration, what's the probability of picking a green? Well, the number of favorable green is 2, and the number of total is now 5. So that's 2 over 5, which is 40%. So here we went with the unrestricted universe of consideration. Unrestricted, it was 20% probability. That's unrestricted. But if we have that condition given bin 5, it went up to 40%. So our probability or chances increased as a result of that knowledge that we incorporated. Yes, I saw wholeness only emptied the contents of bin 5 and not all of the balls from every bin. Okay, so let's continue on and take a look at our conditional probability. So when new information arrives, we know that probabilities are based on observations, and new information can certainly change a probability. And so it'd be useful to be able to evaluate or express the evaluation of a probability that considers different possibilities of new information. Because if we have, in the previous slide, as we said, we had colors, we had another aspect of observation called the bin label. Now, if we knew a piece of information about the color or the bin label, well, that's going to change our universe of consideration. That is new information. And so it's useful in several applications and several domains to be able to evaluate probabilities, to be able to consider what happens if you get certain types of new information. And this is called a conditional probability. And so we have two events, E and A, and these are sets. And you're asking the question, what is the probability of event E given that I have another observation, something is true, piece of information, given that I observe event A. And so we'd say probability of E given A, and that is our so-called conditional probability. So let's take a fictitious example, and let's imagine every week on Tuesday's class or Thursday's class, every week on Thursday's class, when you step outside, let's imagine we're on campus, you step outside, and the moment you get into the courtyard, a pack of dogs runs after you. That's pretty shocking, pretty amazing thing to happen. So we have our probability that you're chased by a dog, and we have sample space omega dog chase can either be true, yes, you're chased by a dog, or no, the dogs aren't chasing after you. So let's say over a 9-week period of time, the first week you leave class on Thursday, step out into the courtyard, dogs chase you. Second week, dogs chase you. Third week, dogs chase you, all the way up to and including over 9 weeks. After a while, you get pretty tired of this, but nonetheless, it's your experience that every Thursday after class, this is your observation. So at that juncture, well, the probability of dog chase, purely from the information, the observations you've made, at that juncture, it's 100% yes and 0% no. So let's say on the 10th week on a Thursday, you begrudgingly and non enthusiastically leave the classroom at the end of Thursday, go out to the courtyard, and all of a sudden there's nothing. So after that 10th observation, well, your probabilities have changed. Your probability now, where it was 100% yes to 0% no, it's now 90% yes and 10% no. So if you were evaluating these probabilities, you would need to be able to pose questions. Is it safe to go outside today? So how you ask that is, well, let me observe the probability that given what I've seen, let me consider this new alternative because that's going to change your probability. And so this conditional probability is a method for evaluating what happens if I have new information available, and that new information available is one of my observations that are possible. What is the updated probability given this changed universe of consideration? Okay, so conditional probabilities are used throughout all sorts of machine learning applications. You like to use autocorrect on your cell phone text message or voice recognition? Well, that's just conditional probabilities. It's computing the probability of the next word given the previous words. In weather forecasting, they're evaluating, for example, the probability of a rain outcome, rainy day, given the previous weather. In robotics, we use this all the time. Something called Monte Carlo localization, you're evaluating the probability that you're at a certain location given all of the previous locations you've visited. So probability is important, but this conditional probability in particular allows us to pose what if this scenario, what if that scenario happens? And now once you know what the new or updated probability would be based on your altered universe of consideration, you can now make informed decisions as to what is the best or lowest probability or highest probability alternative to take. All right. So from the book, definition 2.15, conditional probability of event given event B is the probability that A occurs when event B is known to have occurred or known to occur. So B is a certainty. I know for a fact I saw that Wholeness emptied the contents of bin 5 into the bag. And so given the bin number is 5, it's going to change or filter such that you have an altered or updated universe of consideration. Okay. And we say the probability of A given B is how we pronounce that. So let's get to this conditional probability. From our definition of a straight probability as being the number of outcomes, the favorables in an event or for an event, over the total number of outcomes possible, i.e. outcomes in our sample space omega. And on the right, I have a Venn diagram, and my universe of consideration is my sample space omega at the outset. So there's my sample space omega. All the possibilities are here. So I have my event A, and A could be a singleton event or it could be a complex event. And so I have the number of outcomes in A for my probability, and I divide by the total number of outcomes that represent our sample space omega. So if I do that, okay, well, if I express my conditional probability, probability A given B, what's happening? I said my universe of consideration is changing. So if I say, given that I know B is true or B has occurred, and I'm no longer considering my entire sample space omega, this whole yellow box. I'm only considering that part of omega corresponding to event B. So now that I limit my universe of consideration to those portions that only include event or make up event B, I'm now going to evaluate from that new universe of consideration, I'm going to evaluate the probability that event A is true. So, all right, what is true still from event A if I'm only limited to that part of our sample space, our universe of consideration, known as B? Well, it's this part. Now, this part has a name. I can identify it as A intersect B. It's that region that's common or set of events that are common to A and B. And so I express my conditional probability of A given B is the probability of A and B. That's my number of favorable events. That's A and B here, divided by probability of B. What is probability of B? Well, that's my total number of events. Okay, so this definition is our conditional probability. It is a changing of the universe of consideration to what is given, that condition, on the right-hand side of the condition bar, event B. And when I say given B, I'm eliminating from consideration everything that was outside of that B within our universe of consideration. And so now the probability of the A part is just this overlap region. That's our favorable. And our total is now B instead of cardinality of our sample space. Okay, so this region that is the intersect, and then divided by probability of B that represents the probability, our new universe of consideration. So we still have favorable outcomes over total outcomes. It's just we filter first or set aside everything that is in our new universe of consideration, namely B, event B. So we're given B, and we know the total outcomes is limited to B. And so the condition can be thought of as filtering or limiting the number of total outcomes and therefore changing the so-called universe of consideration. Okay, so here's an example. Let's say you roll a die, a single die. What's the probability of getting a 2 outcome? Well, number of favorable over the total number. Well, favorable 2 is just one item, 1. Number of total, that's cardinality of omega die, which is 6. That's equal to 1/6, which is 0.1667. Okay. If I said the probability of 2 given and even, well, my universe of consideration changes from 1, 2, 3, 4, 5, 6 to just 2, 4, 6. So my number of favorable probability of 2, how many? It's just one of them, 1, divided by the total number. Total number is now 3. That's over 3. The cardinality of my sample space, our reduced sample space, is now 3. That's 1/3 or 33.33%. Let's take a look at the game of poker, a deck of cards. You have one deck of cards, total of 52 of them. You have 13 cards in the same jacket: ace, king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2. And you're going to have all these cards in the spades, as hearts, as diamonds, as clubs. So you can have an ace of spades, ace of hearts, ace of diamonds, ace of clubs, and likewise king of spades, king of hearts, king of diamonds, king of clubs for each one of these cards. So there are 13, 13 times 4, one for each one of the suits. 13 times 4 is 52. So if you said the probability of picking a king, well, how many kings are there? There's a king of spades, king of hearts, king of diamonds, king of clubs. The number of favorable is equal to 4. The total number is equal to 52, which is equal to 1/13. Okay, and that's my probability, whatever that is as a fraction. So let's take this example. You are playing a hand. You have your deck of 52 cards. and you are dealt 3 cards in the beginning, and one card is a jack, and it doesn't matter what the suit is. The other card is a queen, and that next card is a king. So you have a jack, a queen, and a king. And the question you're asked is, what is the probability that the next card that you're going to be given is a king? Okay, well, let's think about this. When I deal the first card, I start with 52 cards. I deal the first card, and I'm left with 51 cards after I deal that first card. Deal the next one, I'm left with 50 cards. Deal the next one, I'm left with 49 cards. Okay, now, of course, when I give out those cards, the total number of cards is 52, then 51, then 50, then 49. Okay, but the number of kings starts out as 4 in the beginning, but when I give out that king, the number of kings available, choices, is now 3. So if I look at this, given jack, queen, king, I know that I have 49 cards left, and of those 49 cards, I only have 3 kings left in the deck. So now my universe of consideration has changed. The total number, NT, is now equal to 49 because I've dealt out 3 cards already. And now the number of favorable, well, I have 3 kings that I can possibly pick. That's now 3. So I have 3 over 49 as my probability. Now, of course, if I didn't know that a jack, queen, and king were given out, well, I have 4 over 52. 3 over 49 is a better probability than 4 over 52. Okay. So again, our condition, it alters or changes the universe of consideration, which is measured as the number of total alternatives that you have. Okay, so let's take a look at independence. And independence talks about the relationship between 2 variables. And so what independence is formally defined as, the probability of A given B is equal to the probability of A. And what that's saying is that knowing event B gives you no information about event A. That means they're not linked to one another in terms of data or information. And so how does this fall out? Well, if A and B there's no information about A that B contains, that means they don't share any events. And if we depict that in the Venn diagram, they're non-overlapping. Here, A does not overlap with B. Okay. So let's kind of demonstrate this also with the definition that we have for conditional probability. We said probability of A given B is probability of A and B divided by probability of B. So if you wanted the probability of A and B, if they're independent, that's just the product of the individual probabilities, and that's a basic property of variables in probability. So we take this product and we notice that in the numerator and denominator, we have probability of B. In the numerator, we have probability of B in the denominator. So those two cancel, leaving probability of A. And so this idea of independence means that conditioning or knowing information about one does not tell you anything about the other. You depict that or visualize it in the Venn diagram as being non-overlapping. Okay, so let's end here and we'll pick back up next time. Have a great weekend, stay healthy, and stay safe.